we only are looking at one coordinate, right? X, there's no y here, right? But t clearly is a function of x, okay? So you could plot t and x on an xy plot, yeah? So the temperature would become the y value, okay? So temperature is a function of x along the length, okay? The bar also is also subjected to certain other influences. So there's, say, a heat flux incident into the bar on the left hand side. Let's describe that heat flux by QA. Yes, let's say QA represents the heat flux that's coming into the bar on the left hand side. And the bar has itself, so if it is made of, a certain material, like, say, steel, then we know that the heat will travel fast along the bar. If say the bar is made of, say, wood or concrete or some other material, like plastic maybe, then we know that the K conductivity would be lower and the heat will take longer to travel the same distance in the bar, okay? So the K is basically the heat conductivity of the material that the bar is made of, okay? We also see this uppercase Q. So we have the lowercase q, which is the heat flux. We have the uppercase Q, which is the say rate of internal heat generation per unit volume. Okay, what does that mean? That means that there could be this bar could be, say, some electrical conductor, right, made of metal or something, and when the electricity passes through this bar, then it will obviously encounter some resistance to the flow. Yeah, there will be some resistance to the flow of that electricity by the material, and that resistance will generate heat. Yeah, so the heat generation will raise the temperature. Okay, so we need to account for that. So Qx is the rate of internal heat generation. So that doesn't have to be a bar with electricity flowing through it. It could be some other bar with, maybe over time it has some sort of chemical process going on in it, and it may be generating or losing heat, absorbing heat because of chemical process. So this Q is basically anything that's happening that's creating heat or absorbing heat. Okay. And then at the end of the right hand side, we have a fixed temperature T that the bar is set at. T as n is n. And the temperature T at x equal to L is T L. Okay, so that is the and obviously the solution would be just finding Tx. Okay, so how do we then represent? So these are all units given. Q is the watt per meter cube. Is usually represented as watt per meter degree Kelvin. Flux per unit area. Heat flux is watt per meter square. Okay. So how do we then understand the physics of this problem? We usually take a little slice of it called dx. That's what we've done here. And we look at the energy conservation along that slice, in that slice. We know that energy cannot be created, cannot be destroyed, that it must be whatever energy enters must also leave, right? Including the energy that's generated. So all of those things should be the energy created, enters, leaving, all of those must sum to zero. Okay, there must be a balance. All the energy that is any energy that's being generated, right? The Qx. Okay, so so in this bar, the flux coming in is Qx. The change of that flux EQX plus EQX, the rate of change per distance, measured distance. Yeah. So EQX over dx times the total change times dx. So that's what EQX over dx times dx means. Yeah. So this is the rate of change of that flux along the distance, and this is the total change. Okay. So this is the addition or subtraction in that flux, which is added to the flux that is flux plus this. Okay. Now we also have this Fourier law that governs heat transfer in a solid. That says that the heat flux depends on the gradient, thermal gradient. Yeah. So the temperature difference between the 2 points determines times the heat flux must be proportional, must be directly proportional to the thermal gradient. So high gradient means high heat flux, low gradient means low heat flux, right? And what's the constant of proportionality? That is K, right? K is the conductivity of the constant of proportionality. So if we know the K thermal conductivity of dt over dx, then we find the flux about the point, right? Qx. Qx is minus k dt over dx. Yeah, so that's the law. Fourier's law of heat convection. Okay? So that all gives us, now for conservation of energy, we must sum all those terms and then set them to zero. So the heat going in is A times Qx, right? Coming out is minus A Qx minus A dQx dx. Okay, let's multiply by the area again. Plus, we also know that there is some heat being created or absorbed, through some chemical reaction or whatever, heat generated or absorbed. So that is A times Qx times dx, the volume. That's volumetric, yes, watt per meter cube. So you need to multiply by the whole volume. Volume is area times the dx, distance. So A Qx dx. And all that must go to zero. Okay? So now you can see that AQX and AQX cancel, and the A itself disappears. You get dQx, the small lowercase plus uppercase qx, the heat generation part, equals 0. Okay? Now, we know that this qx, the flux, is through Fourier's law, is equal to A dt over dx. So we can write it in terms of temperature. You have d by dx, k times dt over dx instead of qx. So you got this plus qx. So that gives you a differential equation. And that's a famous equation. It's called a one-power possible equation with boundary conditions TL equal to TB, Q0 equal to QA. Okay, these are two boundary conditions. Now, why are there? See, the second order. This differentiation applies to this. Clearly, it makes you k to be constant. If the k is constant, then k is d2t over dx squared, right? So it's a second order first degree differential equation. K dx squared plus qx equals 0. Okay, so that hopefully explains how differential equations come out of physical engineering problems that interest us. Okay? This is just one example. This is another one, which is about conservation of electric charge. Okay, so again, I won't go through that. I will let you study it yourself. But while drawing attention form here, that this also this governs the phenomena of electrostatics, how electricity goes from one point to another, how charge transfers from one point to another in the situation of static electricity. Static is the Poisson style equation. Okay, so that's another Poisson. So it's exactly the same form of the equation as this one. One of 1D heat transfer in a bar. You find that similarly you get a similar looking equation for electrostatics. Okay? So, and there are other situations. Maybe you can look for other examples of where the Poisson equation applies. Yeah. So that's the interesting thing about maths, that you just do Poisson equation or just look at one equation, but you can find that it applies to many real situations. Okay. So it's not just Poisson equation. There are other equations, Laplace, Fourier. You may have heard of many others. All of them can be applied to multiple physical problems. Okay. So this is basically just to show where they are coming from. Yeah. So this is an ordinary differential equation that we just derived for heat conduction. Okay. Now, this is just the slide is just showing that if you are given a simple differential equation like this, dy over dx x y squared. Okay. So it's the first order differential equation, first order, first degree. You need one boundary condition, one condition to solve it. Y is 1. Yeah. So because it's first order. So this is actually very easy because you can just separate the variables here. Yeah, you must have done some differential equation solution in your previous maths courses. So if you just separate the variables, 2x and put the dx there, and y, 1 over y squared dy, and integrate both sides, you will get the analytical solution 1 minus 1 over y x squared plus c, the constant of integration. But obviously we are given a boundary condition, so you can put the value of x equal to 0, and that gives you c constant. C comes out as minus 1, right? So y is 1 and at x equal to 0. So c comes out as 1 over 1 minus 1. Yeah, c minus 1. Yeah. So you can, based on that, c minus 1, then you can write y is 1 over minus x squared. So there's an analytical solution for this differential equation, which is very easy. But if we were to solve it numerically, that's what we are interested in, right? We're not looking at it. Okay. So remember the solution. We'll leave that later. So how do we solve it numerically? So the simplest method that we use is called the Euler method. Okay. So how does it work? Well, if you have an initial value problem consisting of a differential equation and a condition, so this Euler method basically applies to initial values. This is first. Yeah? So it applies to initial value problem. That means that the starting value is available. Okay? And you need to find future values. So your dy to the surface integrated is always written for this Euler method. The differential equation is always written in this form. The first derivative, y prime, is a function of fxy. Okay? And y at x equal to 0 is y0. Okay? And that's a critical condition. And that's an initial value. Yeah? So initial value because there is a value at x equal to 0. Right? X, first value of x. The y value is y0. That's why it's called an initial value. Okay? So in numerical methods, as you've seen before, we go step by step. We can take steps from x0, a step, let's say the step size is the same, h, then you can go from x0 to x1, moving h, then move another h, and we go to x2, move another h, we go to x3, okay? So this is typically how we may proceed, okay? In the first step, we compute an approximate value y1, yeah? So we are given y0, x0, y0, that's known, but at x1 we have to find y1, okay? So we need to find a formula so that will give us numerically the value of y1, okay? So that's what we need to do. So in the second step, we compute the value of y2. So then once we get the value of x1 and then get the value of y1, then the second step we find out value of y2 at x2, which is x0 plus 2h. Okay, so that's how we keep moving, where h is the step size. So that is the numerical process of going solving an initial value problem of an ODE, ordinary differential equation. So how do you derive a formula, a suitable formula that will do that job? We again employ the Taylor series. Remember that we did that before in our numerical differentiation, etc. So we can look at this y at x plus h can be written in this Taylor series form: yx plus h y prime x plus h squared over 2. In fact, it's a factorial, and then h cube over 3 factorial, y triple prime, y double prime. Yeah, so the primes being the derivatives. So if one single prime, y prime is dy dx, y double prime is d2y dx, etc. d2y over dx squared, yeah, second derivative, yeah, so we know that symbol, yeah. So from 7(1), we have y prime equal to f, yeah, that is the definition, yeah. This is the form, the given form of the equation. So y prime is the function of fxy. So we have given this y. So y prime is f. So we can write y double prime as in this way, as f prime, which would be a little bit more complicated. So we can write it in terms of f primes. Okay. So so same Taylor series, we can write it in terms of f primes. So yx plus h is equal to yx. Here, that's the first one is the same, and then y prime x, right? H times y prime x just becomes hf. Okay, because y prime is af. Yeah, that is a given. That is your actual initial value problem that you're given. Yeah, that y prime or dy dx is some function of fxy. You're given that. So we get this this simplified Taylor series here, written as yx plus h is equal to yx plus hf, and then you have h squared 2 f prime, h cubed by 3 f double prime. Actually, there's factorials missing, but okay, h squared by 6. Yeah, so 2 factorial, 3 factorial. 3 factorial is 6 anyway. Yeah, so that's fine. Yeah, so this is okay. What we do is where f prime and f double prime, we just evaluate at x and yx. Okay, y function of x. Okay. So as we know that in typically in Taylor series, we typically, because the h is typically, we assume that this is a small step. So when you take squares and cubes of it, then it becomes becomes small. Yeah, if h is small, higher powers of h square, h cube become very small. So therefore we can say simplify. So this is what we have done before. We just ignore the higher order terms. Yeah. So we can say that yx plus h is approximately equal to yx plus hf. Okay. So that gives you a very simplified. F is your function, yeah. So your derivative y prime is equal to your original function, yeah. So so that gives us a simple numerical method. So if you know the y0 and x0, then you calculate fx0. So you use set x. You find the function at x0 and y0, multiply it by your step size h, and add it to the y0, the plus 1, yeah, y0 plus hf x naught y naught, yeah. So that gives you the y1, right? That's the first y. Second, once you get the y1, then you can go and find the second one. So this is a very, very simple formula, right? So y and gives you this general formula: yn plus 1 is equal to yn plus h fx and yn. So so it just multiplies small steps to the function that you're given. Y prime is equal to fxy, right? Okay, so this is called the Euler or Euler-Cauchy method. Okay, simple method, and you can see it graphically very easily. Basically, we may have a true solution like this, but you're approximating that true solution by taking, say, some step h and looking at the slope of that at x0 and y0. These are your starting points, yeah. Y0 value is known. X0 is your starting point. You look at the slope we assume that this slope y prime is that function fx0y0, right? But the true solution may be y equal to yx is this, but we say this h times that function, that slope. Yeah, slope is just dy dx, yeah, y prime, and that is the function, yeah. So we take that slope, we multiply by the step h, and that gives you the next y1. Okay. So, but that may not be the true solution. The true solution may be something like this. So we may, what basically suggests that this step is too large anyway, graphically. So typically we'll take much smaller steps, and we will try we'll try to be closer to this line. Okay. So anyway, so that basically is basically saying that what we do is we just take this y prime as the derivative, the first derivative. We consider it a slope, and based on that, we use it is a slope. Yeah, so we just use some steps, and we keep on moving from there. So this is just an explanation of that. So here, now remember, this is the problem we solved already. We had the analytical solution for this problem, dy dx to y squared. Earlier on we looked at this, y0 equal to 1, right? So this was the original problem, original initial value problem. Yeah, so it's an ODE. So in this case, we need to write this as y prime equal to d. So y prime, which is dy dx, equal to fxy, which is 2xy squared. Yeah. So y prime is 2xy squared. So it is already written in that form that we can use. So what does the Euler method do? Is Euler method saying yn plus 1 is equal to yn plus h fx y. What is fxy? Fxy is 2xy squared. Yeah. So 2h xy squared. Yeah. So that's basically just substituting that in the Euler in this formula. So y1, we just put 0, y2, y1, we put ones here. Yeah. So for then numerically solving this, let's assume some h, some step size h. Okay, h equal to 0.1. Okay, so this is just telling you it must be stressed that the choice of step h is very important. H should not be too small, otherwise the number of steps and round off errors become too large. Yeah, because every time you make a calculation, you also get round off errors. Round off errors are what? Where you neglect a certain number of decimal places. If you have too many steps, you keep neglecting, and then maybe your round of errors gets low. Okay. On the other hand, h should not be too large, because large h implies large truncation error. Because you know the truncation error is what you miss out some of the higher order Taylor series terms. Okay, so that leads to truncation error in each step. So it is not too large, not too small is important. Okay, so you need some experience in determining what h to be used. Okay, right. And there's also obviously an error if you have a large h, then you know that you're calculating the derivative at the wrong place. Yeah, you're calculating the function fx and yn instead of fxn yxn. This is the true place, and you're calculating it here. So that's also an error. Okay, so this method is called first order method. Only the constant term and the term that contains the first power of h are taken. The omission of further terms causes an error, which is truncation. That's what I just told you. Yeah, so omission of further terms causes an error, which is called truncation error. For small h, the third and higher powers of h will be small compared with h square and the first neglected term in 7.3. We therefore say that the truncation error per step is of the order of h square. In addition, there are round-off errors in this and other methods which may affect the accuracy of the values of y1 and etc. as n increases. Okay, so that's just something for you to read. But this is the numerical solution of this problem that we have solved analytically before, and we know the real solution. We know the true solution, so we can see how good the Euler method can be. Okay, so we use h equal to 0.1, right? So we can make a table like this. We can write the steps n0. 0 is the starting point, and you're given x0, y0, and you can write the things you need to h x n y n squared, yn plus 2h n x y n squared. That's your formula, so you can use that, and you can keep writing it here. So that gives you for 0.1. First, your h is 0.1. So the first step xn is 0.1, then 0.2, then 0.3, right? So y1 is y0 2h x0 y0 squared. So you put this formula here, and you keep, and the additions are here. So you keep copying that. Yeah, yn's. You know these first two values. You know. This is your this formula here. So for when you do 0.1, then you're calculating y1. Yeah. So y1 comes out as 1.02. Okay. That's y1 value. Yeah. That's the y1 value by putting in y0 plus 2h x0 y0 1 square. So 1.02. Then you get y2 is this one. You get y3 as you go on. Okay. So this is your y3. Yeah, y1, y2, y3. Okay. So that, yeah, y0 is this, y0.1 is y1, 1.0, y0.2 is 1.02, y0.3 is 1.06162. Yeah, and you can keep going on, obviously. But if we wanted the solution at 0.3, we can put that into the analytical solution. We knew that. If you go to the previous slides, you see the analytical solution, 1 over 1 minus x squared, if you remember. So you put x equal to 0.3 there, and you get 1.0989, which is significantly different from 1.0612. So the Euler method is not very accurate, but of course you can make it more accurate if you reduce the step size. Yeah. So that's just basically another illustration of the Euler method. So we won't go through that too much. You can read it yourself. Just what it does. Okay. One of the things that you may need to do, if you are given an equation which is not of that form, you must convert it into that form. So if this, say, if you're given a differential equation like this, dy dx plus 2y 1.3 e to the power minus x with y0 equal to 5, then you must rewrite it as in this form, dy dx equal to 1.3 e to the power minus x minus 2y takes the other y on the other side, so that you get this, always get this form. Yeah, y prime equal to function of xy, okay, with some condition. Yeah, so that's always the case. So f function of xy is, in this case, is 1.3 e to the power minus x minus 2y. Okay, that's your function. And now this is another example. A ball at 1200 Kelvin is allowed to cool down in air in an ambient temperature of 300 K, assuming the heat is lost only due to radiation. The differential equation for the temperature of the ball is given by this. Yeah, so this is the rate of change of temperature with time. Okay, based on this. Typically, this will give you some kind of constant, Stefan-Boltzmann constant, and some other values like volume of the ball and all those kind of things, surface area of the ball, all those things will come in, and etc. And then you have this T4 theta, the ball temperature, theta 4 minus the ambient temperature 300 to the power 4. Yeah, so the radiation fourth power law. Okay. So that's basically how this may be derived, but you're given that. So we just assume that this is what it is. This is straight. This is y equal to function of xy type thing. So theta is equal to function of theta and t. Okay, time in this case. Okay, so theta is the temperature. Okay, so find the temperature at t equal to 480 seconds using the Euler method, assuming a step size of 240. So 240 steps later, find t equal to 240 and find out in 2 steps what the temperature would be, the theta would be, based on this differential equation numerically using Euler method. Okay, so that's what we do. We have this d theta over dt, that is the actual statement of the problem. We are already given that, which is a function of theta and t time, right? That's your ft theta. Okay, although time doesn't appear there anywhere, but it's still dependent on time, we know. So theta I plus 1 is theta I plus fti theta I times h, which is just the formula. And so first values are I plus 1, you just put I equal to 0. So this is 1, 0, 0, h. So 1200 plus function of 0, 1200 times 240. Okay. So 0, 1200 is you just put in the values of time and 1200 temperature. So it's only the 1200 temperature that you use. So you go there and you get 106.09 Kelvin, which is the temperature at theta 1. Okay, that is theta at 240 is 106.09. Okay, now the step 2, because you wanted temperature at 480, so you need another step. So now you put I equal to 1, T1 equal to 40, theta 1 equal to 6, and so you put these values 106.09, so you put these values there, and you get theta 2, 110.32 K. So theta 2 is the approximate temperature at 480, 110.32 K. Okay. The first one 100 was 106 and 09. Doesn't look correct because the ball, instead of cooling down, is heating up. So that means the step is too large. Okay. But anyway, if you can get the exact solution for this, which is a relatively simple differential equation to solve, the exact solution comes out as 647 at 480, 647. So significant difference. See, 110. So that means the step was too large. So if you look at this solution, this is the exact solution. The reduction in temperature. In this case, the Euler method gives you much worse value. Okay, so because it cooled so much so that it had to heat up later, right? So this was completely wrong. But you can reduce the step size. So if you take just one step, the error would be 252%, very, very large. 240 we already did. The error is 82%. But you see, if you reduce the time step, reduce this. It is a time step. It's 120 seconds. Then the error is only 15%. If you reduce it to 60%, 60 seconds, it's 5%. If you reduce it to 30 seconds, it's only 2%. Okay, so the method does work, but steps start. So here it shows you how if you have just one step, this is 2-step solution. This is with 4 steps of 120 to 480, and if you keep reducing it, you see you keep coming closer to the solution. Yeah. So the first one is very bad. Second one is this one, quite bad. Third one is starting to come close, but you can work it out. Okay. So effect of step size. So this shows you convergence. So this was the temperature when you calculated it with the large 480, just one step. This is 2-step. This is 3-step, and then this is the correct value, right? When the step size is 0. But you see that even with a much bigger step than 0, something like 30 or something, right? You still come close to a very good solution with Euler's method. So the Euler's method does give you, this is the exact solution. The Euler method gives you a reasonably good solution. You're converging to that exact solution with reducing time step. Yeah. So that's a property of the method, which is what we expect, right? So we can see the Euler method can have large errors, and you can see that by illustrated with the Taylor series. Yeah? So that's what we are actually doing. So it's only the first, these 2 terms we are picking up. All this is being ignored, and that's why we get this errors. Okay. So moving on, there are some. There's just one example problem here in the tutorial that you can use the Euler method to solve. Okay. My colleagues are going to join in soon by 2:30 to help you with the tutorials of both lectures 13 and 14. Okay. Hopefully this has been clear. It's a very simple method. Just applying this formula. Yeah. You write the equation in this form, y prime equal to xy, and then just apply this. Write this y prime is equal to function of xy, and then yn plus 1 is equal to yn plus h of xy. Yeah, so you just keep because y prime is a slope, right? You see, you multiply that slope with some small increment, small distance h, and then you get the. Any questions? Anybody? Okay, so I think Dr. Khan is here.
Yeah.
Mustafa, you are here?
Yes, I have joined and I can carry on with the tutorial.
Yeah, so I have managed to finish the lecture 13 and 14 today. So you have those lectures,
Yeah,
right?
Yes.
Yeah, and it's also the PDFs are all in the
content
calendar as well.
Yeah.
In the calendar as well. Yeah. So both lectures actually dealt with different topics. The first one was regression analysis, and the second one is the Euler method for solving ODEs. Yeah. Initial value problems.
Yes, sir.
Okay. So hopefully they and there's only, I think, 2 tutorial problems there. So if you can maybe just go through them for students to understand.
Yeah, sure.
Yeah. Okay. Thank you very much. Thank you. So I will disconnect unless there are any questions. Anybody with any questions? Okay. I'll let you carry on. Thank you.
Right.
Bye bye. Bye bye.
Hello everyone. Today we are going to go through the tutorial problem for lecture number 13 and 14. And as Professor Usmani told, that lecture number 13 was related to the problem related to the regression. So the first question is, it is about the linear regression, that the number of revolutions per minute, which is x, the time is given in terms of x, and power y in horsepower HP of a diesel engine is obtained in the following table. So at 400 revolutions, the horsepower generated by the diesel engine is 580 horsepower. At 500 revolutions, the horsepower generated is 1030. At 600, the diesel engine is generating around 1420 horsepower. So this is the information about the diesel engine, where the number of revolutions has been given and the corresponding horsepower has been given. So in that question, what we need to do, we need to fit a curve, fit a line for this data, the line which is representing this data. So in the part first, it is asking us to find and graph the simple regression line for y on x. So to do so, as you know that these are the x values, the number of revolution as given in the question, and corresponding horsepower values are given as y. So we need to fit a line between this x and y. So what we are going to do, we need to first find out the squares of x values. So this is what we have done in the first, in this column. The square of 400 square has been found out, and which is going to be this. And similarly, square of 500 is this one, square of 600, 700 and 750. The square values of x has been found out in the first column. And in the second column, we are finding out the square values of yj. We are finding these square values because we know that when fitting a linear equation, these square values would be used in the formula. That's why we are finding out these square values. So square values of y have also been found out, and then the multiplication of x and y values for each entry. For example, for the first entry, it would be 400 times 580. For the second entry, it would be 500 times 103. So this is how we can find out this third column, which is xj times yj. So we have found out all these auxiliary values as per this table, and now in the bottom row, as you can see here, we are finding out the summation of all these values. This is the sum of xj and yj. This is the sum of yj square values. Sum of all these 5 values, 1, 2, 3, 4, 5. Sum of all these 5 values would be this one. And similarly, sum of the square of x would be this one. Sum of yj would be this one. Sum of xj's would be this one. So up to here, it is very straightforward. We just need to find out the values as per this table. So to find out the equation which is fitting this data has to be fitted into the equation. So the number of readings, the number of values which has been provided to us are 5. N is equal to 5. 1, 2, 3, 4, 5 data points have been given to us, and using these 5 data points, we find out the linear equation which is fitting these 5 data points. So what we are finding out the x bar as per the formula which we would be using to find out s1 square and sxy. We would use the values such as xj square. We would be using values such as x bar and y bar. So x bar is nothing. X bar is the average of all x values, and the average of all x values is summation of xj's divided by n, which is 950 divided by 5. This is what has been calculated here. And similarly, we need to calculate y bar, average of y values, and that would be 1402. So now we would be finding out s1 square and sxy. As you can see in today's lecture slide, today's lecture would be here. So to find out a linear equation fitting a number of points, we need to find out this variance of x, which is s1 square, and covariance, which is sxy. So these two values we need to find out, variance and covariance. So s1 is variance of x, and according to the formula, it is 1 over n minus 1, and summation of xj square, which would be nothing, xj square would be this 182250. This value would be summation of xj square, which has been used here. Then 1 upon n, which is 5, times summation of xj and to the square. So xj, summation of xj is 2950, and square has been done according to the formula. So we get a value for s1 square. This is the value for s1 square, which is the covariance of variance of x. Now we need to find out covariance, and the formula of covariance is 1 upon n minus 1, which is 1 upon 4 here, summation of xj by j, which is calculated here in this table. This is summation of xj by j. Here, summation of xj times summation of yj, which is 2950 times 7010, which has been written over here. 2950 times 7010, and over n divided by n, which is 5. Right? So this gives us the value of sxy. So we got both of these values, s1 square and sxy. And now these values can be used to find out the slope of the line which is going to be fitting in these 5 data points. So the slope of that line would be nothing but b is equal to sxy over s1 square. And you put in the values of sxy and s1 square in this formula, and we get the slope as 4.3. Slope is 4.3 for this line, which is going to be fit in the 5. Formula is y minus y bar is equal to b times x minus x bar. And according to this formula, y minus y bar can be taken from this table, which we have calculated earlier. Y bar is 1402. So y minus 1402 is equal to slope times x minus x bar. X bar is 590. So the equation of the line which will fit the above 5 data points is this. So this is how we can find out a linear equation which is going to be fit in a given data points. There were 5 data points which were given to us, and we were asked to find out a line which is going to fit through those 5 data points, and this is the procedure to find out that what is the equation of a line which is going to fit certain data points. And now in the second part of the question, we have been asked here, we have been asked to determine the Pearson correlation coefficient. So the Pearson correlation coefficient, you must have studied in today's lecture, is R. R is equal to sxy divided by under root of s1 square and s2 square, where s1 square is the variance of x and s2 square is the variance of y. So similarly, as we have calculated s1 square using this formula, so we would calculate s2 square using the formula here on your screen. So the formula for s2 square has been used here. So yj square value has been taken from the table, which is 11358100. This is yj square. Sorry, this one is yj square. This value is yj square. This has been taken from the table, then the value of yj, and then squaring it. The summation of yj is 7010. That has been also has been taken from the table, and we would get 4s2 square is this, and s2 square is 382520. So now we have sxy, we have s1 square, we have s2 square, and we can easily find out the r value, which has been asked in the question. We have been asked to find out the Pearson coefficient. Pearson correlation coefficient, which is r, can be calculated using this formula. So plug in the values of sxy, s1 square and s2 square, and we would get r is equal to 0.99968. So this was the first question of today's tutorial, and now in the second question, it is exactly the similar type of question, and what we need to do, we have been given different data set, and we need to make a linear equation through which can pass through these points, or which can satisfy this data. So repeat the last problem with the following data table that measure deformation in millimeter and Fresnel hardness Y in kg per millimeter square of a certain type of steel. This data which has been shown to you in this question is about the hardness of the steel according to the deformation. At 6 millimeter deformation, the hardness of the steel is 68 kg per millimeter square. And at different deformation values, such as at 26 and 28, different value of Fresnel hardness has been given to us. And then we need to find out the equation which can fit to these data points. So we would follow the similar procedure. First, we need to find out the auxiliary values. And in the auxiliary values, first we would find out the square of xj values, as we did in the last question. Then we would find out the square of yj values, exactly same as we did in the last question. And then we would find out the product of xj and yj. Here, product of xj and yj. 9 times 67 for this, 11 times 65 for this. These are being multiplied. When I say product of xj and yj, they are being multiplied. So once we get these auxiliary values, then we would get the sum of these values. Sum of xj square, sum of yj square, sum of xj yj, sum of xj and sum of yj. Now again, we repeat the same process, that we would find out the mean of x values, which is 20.33 millimeter, and mean of hardness values, which is 48.88 kg per meter square. And now we would find out S1 square, which is nothing but 1 by n minus 1 as per the formula. As you can see, the formula of S1 square is 1 upon n minus 1 times summation of xj square minus 1 upon n, summation of xj and square to that one. So this is what we are doing here. This is being put in here, xj square, and summation of xj is 183, and 183 square is here, and divided by n. So we would get S1 square as this value, 944 divided by 8. And similarly, sxy would also be calculated using the formula provided in the lecture notes. 1 by n, summation of xj yj, this value, which is 7701, then summation of xj, summation of yj, 183 times 440 divided by n would give us this value. So now we have S1 square, we have sxy, so we can find out the slope of the line, which is nothing but minus sxy divided by S1 square. So we got the value of b, we got the slope of this line, which is minus 1.319. And similar to the last question, we are going to find out the equation which is going to fit these data points and having a slope of minus 1.3. So the equation which we are going to use would be y minus y1 is equal to b times x minus x bar. So y minus y bar is the mean of hardness values, which is 48.88 minus 1 point is equal to minus 1.319, the value of b, slope, and x minus x bar would be 20.33. So using this equation, we would get the equation of the line which will fit these data points. So this is the line. And as we did in the last question, we also need to find out the Pearson correlation coefficient, which would be r is equal to sxy under root s1 square s2 square. So we already have sxy, we have s1 square. We would find out s2 square. So s2 square would be according to the formula can be found out here, which is summation of yj square minus, this is a typo here, this should be 440. This is yj square, yj, summation of yj, then square divided by n. So value of S2 can also be found out using this relation, as you have seen here. So now we have all the values required to find out the Pearson correlation coefficient. We have S1, we have S2, we have Sxy. So just plug in these values in this formula of Pearson correlation coefficient, and we would get a coefficient of minus 0.97288. So these two questions were very similar to each other, and in these questions we were asked to find out the equation of a line which can fit a certain number of data points. In the first question there were 5 data points, and then in the second question there were 9 data points, and the process of finding out the equation of the line is the same for both the questions. So this was about the linear regression and how to find out the equation of a line which can fit a number of data points. So if you have any doubt, you can ask, and if you don't have any doubt, then we can proceed to the tutorial problem, which is based on the Euler's solution to differential equation. So everything is okay. Now we would move to the next problem, which is at the end of today's lecture. So in this problem, we need to solve a differential equation. But what this problem is saying to us, it is saying that in many daily control system modelings, differential equations are often used to describe the behavior of the required process control. So a system is described by the non-standard differential equation. So any system, it could be any system, it could be water supply system, it could be sprinkler system, it could be any system in a building which is governed by using a differential equation. And in those kind of cases, then we would find out the solution of the differential equation. So here in this case, a system is being governed by this differential equation, which is x square times dy by dx minus xy is equal to 1 over y. And the initial condition for this differential equation have been given, which is at x is equal to 1, y would be 0. So if we put in the value x is equal to 1, we would get y as 0. This is the initial condition, which is differential equation. So in the first part, what is being asked to us to use the substitution y is equal to under root z, and write down dy by dx in terms of z and dz over dx, and so dz over dx is 2z over x over x squared. So what we are going to do, we are going to assume that y is equal to under root z, and then we need to find out what this equation is like. In this equation, we would replace the terms which are in y. So what we would replace y with under root z, and we would replace dy by dx with something which has dx and dz. So if we differentiate this equation, y is equal to under root z with respect to x on both sides, what we would get dy over dx on the left hand side, and on the right hand side we would get 1 upon 2 under root z, which is the differentiation of under root z, times Yeah, it's the chain rule to, or on you can say it. You can directly differentiate under root z, because see, under root z is nothing. It is z to the power 1 over 2. So when you differentiate any algebraic function such as x square, so it would be 2x. The differentiation of x square is 2x. So similarly, the differentiation of z to the power half would be 1 upon 2 times z to the power half minus 1, and which would be 1 upon 2 under root z. This is what we have done here. And since it is a function of z and we are differentiating it with respect to x, so dz over dx would also come, or you can apply the chain rule which has been given here, which is dy by dz times dz over dx, right? So dy by dz can be easily find out, which is this: y is equal to under root z, and dy over dz is equal to 1 upon 2 root z. So this can be placed in here, and we would get this one. So you applying the chain rule, we would get dy over dx is equal to 1 upon 2 root z times dz over dx. So this equation can be rewritten as, if we plug in the value of dy by dx in terms of dz over dx. So we get, let me erase all of it. So here we get dy over dx is equal to 1 upon 2 root z times dz over dx. So we plug in this value here in this equation. So we get x squared times 1 over 2 root z times dz over dx minus x. Now we put in the value of y as root z, and is equal to 1 upon root z. So this is what we are getting in here. So this equation can also be rewritten as, we move in this to the right hand side. So dz over dx is equal to 1 upon root z plus x root z, and this value would be in divide, x square 2 root z. So this would give us this equation. If you multiply with 2 under root z over x square with this bracket, you would get the same equation. And the initial condition which has been given to us at x is equal to 1, y is equal to 0, has changed to this one, because at x is equal to 1, y was 0. So at, you just assumed y is equal to under root z. So y was 0 at x is equal to 1. So at 1, 0. So z becomes 0. So at x is equal to 1, z is also 0. So this is the initial condition, the new initial condition as per this new differential equation, as you can see here, because we were asked to find out the initial condition for this differential equation. So that's why the first part is done. We found out the initial condition as well, and the modified new differential equation. So in the second part, it is saying that use Euler's method with h is equal to 0.1 and approximate z at x is equal to 1.3, the solution of the equation. So of equation 5.2. So we need to find out the solution of this equation which we just have derived at x is equal to 1.3. So what we are going to do, so according to Euler's formula, Zn plus 1 would be equal to Zn value plus h, which is the interval, times function of x and Zn. So Zn, first we would start with the values of x naught and z naught. So the x naught value here is 1. As you can see, x value is 1 everywhere. The initial value for x is 1, and x naught is equal to 1. The value of z is 0 as per the new initial condition. So we need to find out z1. So z1 would be zn, which is 0, plus 0.1, because we need to assume h as 0.1, bracket 2 over 1 plus 2 over 1 square, which is nothing but dz over dx is equal to 2z over x plus 2 over x square. It's coming from this equation. So 2 zn was 0, 2 times 0 divided by 1, because x is 1, plus 2 over 1 square, because x square. So we would get z1 as 0.2. So now we have x1 is 1.1, because h is 0.1, and x1 becomes x naught plus h, which is 1 plus 0.1, 1.1. So x1 is 1.1, z1 is 0.2, which we just have calculated, and we need to find out z2. So z2 would be z1 plus h times 2 times z1, which is 0.2 z1, divided by x1 plus 2 over x1 square, and we would get z2 as 0.4. Similarly, we would find out, using the value of x2 and z2, we would find out the value of z3, and z3 is the value at x3. x3 is 1.3. So at x is equal to 1.3, z is equal to 0.60748. So at x is equal to 1.3, z is 0.60748, and this is what we have been asked to find out. Z at x is equal to 1.3 using the interval h is equal to 0.1 and ILS method. We were asked to find out the solution of this equation 5.4 using this information, and this is what we have done. We have found out the solution of the equation at x is equal to 1.3, and which is coming out to be 0.607483. And in the third part, the final part, we have been asked what is the corresponding approximate solution to the equation, which is T751, the original equation at x is equal to 1.3. So the approximate solution would be y at 1.3 would be the solution, and y at 1.3 would be nothing but, because we know that y is equal to under root z. So at x is equal to 1.3, y 1.3 would be under root of z at x is equal to 1.3. So at x is equal to 1.3, what was the z? At x is equal to 1.3, the z value is 0.607. So y at x is equal to 1.3 would be under root of 0.6074. Y at 1.3 would be 0.779, which is this value. So this is the approximate solution, and we also have been given equation to find out the exact solution. To just plug in the value x is equal to 1.3, we would get the value of y as the exact solution. Just put in the value of x as 1.3 in that equation, and we are getting the exact solution of the equation. Y at x is equal to 1.3 would be equal to 0.7834. So this is the exact solution, this is the approximate solution, and we need to find out the error. Just subtract these two values, and this is the error between the exact solution and the approximate solution. So this was about using the ILS method to find out the solution of differential equation, and in the first part we substituted the value of y in terms of z, and then found out a new equation with new initial conditions. And in the second part, we found out the solution of that new equation. And in the third part, we found out the approximate solution of the original equation using the information which we calculated in the second part. In the second part, we calculated the z value at x is equal to 1.3, and we found out the solution. We found out the solution of the original equation, which was in terms of y at x is equal to 1.3, using the information which we calculated here. So this was about the tutorial of today's lectures, and there were only 3 questions in today's tutorial. And if you guys have any doubt or any question, you can drop in your message, and then I would be happy to answer. So I guess there is no. Is there a question? If someone is typing. Okay, so this is it. Thank you for attending the lecture and the tutorial, and see you in the next lecture.